All right, I've had some questions every now and then from some of my tech school students about what are the problems like when you get into a 4-year program. So I wanted to give a little demonstration of it's probably actually one of the simpler problems that we would have to deal with, in a baccalaureate type of circuits class. So, we're given something that looks fairly familiar. It's just a mesh circuit with a couple of reactive components. And we've solved circuits like this in our classes many, many times. But there's going to be some differences in the initial conditions that we're going to be working with. And the other thing that we're going to deal with is this switch. So the way this circuit is set up is when the switch opens, what's going to happen? Well, when the switch opens, it's going to take away a short that's across R2. And the circuit then is going to go through a rebalancing process as it goes from one steady state condition to another steady state condition. And we want to look at what's going on in that rebalancing process. So it's not just the simplest possible question, like what's the voltage across a specific component. We're looking a little more in depth as to how the circuit functions. So in addition to that, one of the other things that we have to deal with is that the initial conditions, the voltage across the capacitor, for example, here is given, and the voltage across the capacitor is this mess right here, which is a time dependent. It's based on two things. It's based on the amount of time, and it's also based, since we're using E here, what E is kind of a function of natural decay. So when we talk about the E, the little e, we see it a lot because when we talk about how a capacitor charges and discharges, it's the same curve that, I don't know, to pull something from completely out of left field. It's the same kind of curve that you get when a group of people start to get the flu. There's a whole bunch of people that at the beginning get it, and the curve is very steep, and then the curve starts to flatten out as there are less people available to get the flu. So that's called a natural, it's a part of the natural logarithm. This is a natural exponent. So it has to do with the nature of things, which of course leads us into how materials work and how atoms of different materials coexist. And when we're talking about electrons flowing through a wire, that's exactly the type of thing we're talking about. We're talking about how the current and voltage change during the time between those two steady state conditions that we talked about here. So we're given the voltage across the capacitor here, and we are given the inductor current here. And we're going to use those two things to prove that KVL and KCL work or hold true. Let me go ahead and get a red pen here. You know how much I love my red pens. That they hold true, plus minus around this first mesh over here, the source mesh, and then also Kirchhoff current law here at node B. So we need to prove that throughout that transitionary period that Kirchhoff's voltage law and Kirchhoff's current law are held true, and we needed to do it with these funky voltages down here. So let's move on to slide number 3. We're going to go through this step-by-step process, which really is exactly the same process that we would go through if we were solving this with simple voltages and steady state conditions. So we'll go through the same process. Elements of this should look familiar to you as you watch and play along at home. So the first thing we're going to do, get the voltage across the inductor. The voltage across the inductor, VLT, is equal to the LDI dt, which is equal to 3, because the inductance is equal to 3 henries. So we'll plug the 3, and then we're going to take the differential or the derivative of this here, and that is going to give us, we're going to take that 2.1 and pop it down here. We're going to take that minus 15.9 and pop it down here. This is just the mechanics of something that you would be studying in your calculus classes, as you would be taking them concurrently with this in a 4-year program. So I'm going to be taking those kind of shortcuts, just showing you the mechanics of what we do, but I'm not going to explain how derivatives work. You'll get that when you take calculus. But at some point we get down to something like this, and we can do a little bit of multiplication, and after all is said and done, we end up with a value, a funky looking value with a bunch of exponents, but it is a value for the voltage across the inductor. So now we have the current through the inductor, and we have the voltage, which means we could calculate the reactance of the inductor, but we don't really care about that at this point. We're simply looking to try to figure out what all of these voltages and currents are. We now have the voltage across the inductor. It's negative 6e to the minus 2.1t minus 2e to the minus 15.9t volts. Boy, that's a mouthful. Let's move on and look at the capacitor current. Capacitor current, we calculate that similar to the way that we calculated the inductor voltage, in that we take C dV dt of Ct based on time. The value of the capacitor is 1 over 75 farads. That's an interesting way of presenting it. Not in the traditional micro milli farads, but just as a raw fraction. 175, then we've got the rest of this where we're going to take the derivative like we did before, which means we'll take the minus 2.1 and pop it in the middle here, and we'll take the minus 15.9 and put it right in there as we see here and here. We'll do our multiplications, and we come up with the capacitor current based on time can be calculated as this value right here. We can simply plug in any value of t between the two steady state values and determine what the current through that capacitor is at any time. So that is a really convenient thing to be able to do. That takes care of number 2. And number 3, voltage across R1, V is equal to I times R via Ohm's law. We probably don't need to do all that because we actually know that the voltage across the inductor, we know what that is. We know what the voltage at the source is. So we can simply use Kirchhoff's voltage law to determine what the voltage across R1 is. So VR1 is going to be equal to 12 minus the voltage across the inductor. So that's 12 minus negative 6 e to the minus 21 or 2.1 t, all that stuff that we just calculated over here. And we can calculate from that what the voltage across R1 is. And the voltage across R1 is given right here. So we now know the voltage across R1. Last thing on our list is the currents through R2 and R3. And I cut this off a little bit. Oh, well, we'll just have to live with that. So IR2 is equal to the voltage across R2, which is the voltage here, minus the voltage across the capacitor, divided by 6 ohms. So that is going to give us this here, VR2 minus VC divided by the 6 ohms. There's going to be a lot of work to be done here, but it turns out to be this. IR2 is equal to this many amperes. Similarly, I is equal to V over R. We can calculate the current through R3, which is right here, because we need that to figure out what's going on with Kirchhoff's current law here. So we've got all 3 currents now here, IR2, IR3, and we have the capacitor current. So we'll be able to prove that. We have the voltages here across the inductor. We have the voltage across R1, and we have the source voltage. So we have everything we need to prove Kirchhoff's voltage law in the source mesh. So moving on to step 6, let's look at the source mesh. The Kirchhoff's, let's do the walking around thing we do in class. Start here, minus 12 plus VL plus VR1 must be equal to 0. So let's substitute in what we have over here for the voltage across the inductor, and we'll substitute in here what we calculated for the voltage across the resistor. We can look at this, and we can see that we've got plus 6, minus 6. These guys cancel out. The 12s cancel out. We're left with 0 equals 0. So energy is conserved, and Kirchhoff's voltage law holds true in the source mesh. So that takes care of the first part of the question. The second part of the question says, is Kirchhoff's current law valid at node B? So we don't have any current here because the switch is open, but we do have a current through R2, so resistor 2 current. We need R3's current right there, and we need the capacitor current right here. So we have all of the information that we need. We simply have to say, is the current through the resistor, IR2, equal to the sum of the current through the capacitor and the sum of the resistor 3. And if they are, then this equation here must equal 0. So let's look at what we have. Here is all of that information. IR2 is equal to the capacitor current plus the resistor current. Okay? Notice that, of course, the exponents are all the same here, so we can just add these two together and these two together and come up with the answer. And what we have is, on this side of the equation, we have 0.45 and 0.12 as our coefficient, and on this side, we have 0.45 and 0.12 as our coefficient. We also have the 1 on both sides, so the left side is equal to the right side. That proves that Kirchhoff's current law holds true, energy is conserved, and the amount of current flowing in is equal to the amount of current flowing out. So we were able to solve this problem using the exact same methods that we used in our circuits classes, with a few things that were added to the mix to make it a little bit more challenging. And quite honestly, it's really a question of housekeeping. We didn't do anything new here. Maybe we looked at a couple of exponents and we learned a little bit about the E exponent, the natural exponent, but really nothing new under the sun. We still stood by our old standard Ohm's law and Kirchhoff's law, and those three things, Ohm and the two Kirchhoff's laws, are what actually saw us all the way through to this solution. So anyway, thought it might be fun to have a look. We'll see you next